Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but you know, I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah.
Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Or at least the most popular places.
Well, yeah, the most popular ones. I suppose all the normal popular ones, if you want to say. So
yeah. Spotify, Apple,
Google,
Google,
YouTube, everywhere.
YouTube, Audible. So we have it there.
Yes.
Well, welcome everybody to another episode of Ask Us Anything about Electrochemistry. I'm Alex Peroff. This is my colleague, Dr. Neil Spinner. And during these live streams, we try to answer questions that you have about electrochemistry. So we've been doing this for a while, and I'm going to go over the boilerplate stuff. Maybe you've heard this before, but it's actually been changing a little bit as either more people listen to us or ask questions. But we tend to, we get a lot of questions from YouTube, on Twitter, and emails and phone calls and stuff like that. So this is the time that you can spend to ask us questions in a little bit more detail, so that we can try to help you understand electrochemistry a little bit better. In general, questions that are best for this type of platform are ones that are not ultra broad, just like what is electrochemistry and explain, cyclic voltammetry or EIS to me. Those are for webinars, and Neil has a lot of webinars that he has done on our YouTube channel, and you can access them by becoming a tier 2 YouTube member. So if you have a question about what is EIS and understanding the basics, we'd encourage you to watch those. I mean, it's hours and hours of content on how EIS
Who
works.
wouldn't want to watch hours and hours of me?
I know, explaining EIS.
The answer is nobody, by the way, but I appreciate that.
But then at the same time, if a question is too specific, then we're going to have absolutely no idea what it is, because you're asking about the activation energy associated with outer, some kind of overpotential deposition type of thing, and we're just going to have no clue. But questions where you're trying to understand conceptually or even perhaps mathematically how to calculate something that might be in our wheelhouse, that's the best type of question to ask during these live streams. We are on Restream. That's the broadcasting platform, and we're streaming to YouTube as well as Twitter or X. And so if you want to join us on the on Restream to ask a question or show us your data so you can talk to us, there should be links. If you are a tier 1 or tier 2 member, there will be a link in the YouTube community chat that will allow you to join us on Restream. So that's another thing for tier 1 and tier 2 YouTube members. We're going to do this for about 2 hours. We usually have a live stream for 2 hours. If you are unable to watch the live stream now, so you're watching this later, there will be timestamps in the description below so you can see all the questions that were asked. Also, please do not spam the chat with anything. First off, anything that's not electrochemistry, and keep it very, PG, sort of say. Nothing political, nothing crazy, no random off-topic things. Just ask electrochemistry questions. And if you are really curious about an electrochemistry question, do not spam it. Otherwise, we will probably block you. If we have been answering questions and we forget yours, you can give us a gentle reminder later. So just a couple of things we've noticed, as we have occasionally gotten some spam. So please keep that to a minimum. Lastly, we apologize in advance if we mispronounce anybody's name, because it's just whatever you put in for your for your YouTube or your Twitter handle that we'll actually see. And I think with that said, that's all the boilerplate stuff that I usually give. So let's start looking at some of the questions that we've gotten. So we got a question from Divya. I might be again mispronouncing it. Hello there. In EIS graph plotting, if I don't get a semicircle followed by a spike, instead I get only an arc, how do I get to know the bulk resistance in such cases? She continues to say, also, could you please elaborate the possible pattern of Nyquist plot and what to infer from them, especially the bulk, especially the bulk resistance. You want to go?
Sorry,
you're
that
the
wasn't
EIS
like
guy.
that wasn't a like, oh, why don't you stop talking? Clear throat. I was actually just clearing my throat.
Oh, okay.
No, I can answer this question. So the first thing to say is, we were just talking about this. I think by bulk resistance you mean what people call, I mean, there's a million terms for this, either uncompensated resistance or series resistance or something like that. So I believe that's what you're referring to, which is to say that it's distinct from what we might call the charge transfer resistance. But I'll try to answer your question, the first question and the second question kind of combined. So if we have a Nyquist plot, right, we have Z real and we have usually minus Z imaginary. All right. So your first question was something like, when I get a semicircle, right, as opposed to a semicircle with a spike. So I assume that this is sort of what you're talking about. You're saying when I get this red one instead of this blue one. So the main thing to be aware of is that if you're just looking at bulk resistance, either of these plots that you might get are it's the same thing. Okay, so I'll identify a few things. So on a typical Nyquist plot, let's say this point here is actually 0, 0, right? Like right here. This is the origin of the plot. The bulk resistance, again, series resistance, ohmic resistance, uncompensated resistance, whatever you want to call that. I'm going to call that R0, just for my own made up purposes here. That is effectively the distance on the x-axis, the z-real axis, from the origin to where the points intersect. So whether you have a straight up and down line, which would be a capacitor, whether you have a semicircle and some Warburg, or a capacitor, or you have whatever you have, wherever this starts, intersects the x-axis, that is effectively what you would call bulk resistance, or ohmic resistance, uncompensated resistance, etc. The next, and again, this is sort of more now to your second question, which is to say interpretations of a Nyquist plot. So very generally, if I have a semicircle, it typically refers to some kind of charge transfer process, and the width of the semicircle on the x-axis, the z-real axis, is roughly equivalent to the charge transfer resistance. Okay. The equivalent circuit for the red one here would be something like this. So this would be my R0. And then I would have, I'm going to draw a capacitor for simplicity here. You might have a constant phase element if you have non-ideal capacitances, but this is like double layer capacitance and charge transfer resistance. All right. So this is like the simplest circuit that would be if I have bulk or uncompensated resistance right here, and then I have some charge transfer process in parallel with double layer capacitance. The blue one would be the same thing, except I would have, sorry, not there. The same thing, except I would add in a Warburg element right here, right? So that's sort of a common kind of representation of diffusion, is where I'd put a Warburg in. So this bottom part here would be RCT and a Warburg. So I'm sort of shorthanding this just for quickness and simplicity. But you can imagine putting this in here, you have that extra Warburg element on the bottom part of this circuit. That might be something like that. But basically, the resistances are the easiest things to directly extract from a Nyquist plot, because you can visually find them pretty easily. And the bulk / uncompensated / ohmic resistance is directly achievable by looking at the high frequency intercept on the x-axis of your Nyquist plot. Okay, so that is it. Now, all of the rest of the answers to this question fall pretty squarely under that thing Alex just mentioned, which is I have a webinar talking about a lot of this, right? So I have a 5-part impedance webinar series. I go into a lot of detail about like a lot of other parameters that you can extract in impedance, on a Nyquist plot, about what happens and why. There's a lot more details for sure. So I would encourage you to, maybe try to check out some of those webinars for longer form content. Beyond just a little bit of those sort of quickest, answers about what you can get out of a Nyquist plot pretty easily, including, to your question about bulk resistance. So hopefully that kind of at least gets you started.
All right, very good. So Barry has a question.
Welcome back, Barry.
Welcome, Barry. Yeah, welcome back. Always good to see you. Also, I'm glad that he enjoys the podcast. Fantastic.
Thank you.
So Barry's asking, how do I think know if some reaction is EC-CE or E1-E2? What to do? So I'm going to try to tackle this a few different ways. So when you say, and please correct me if I'm wrong, Barry. So when you say EC and CE, you're talking about an electron transfer step followed by a chemical step, or a chemical step followed by an electron transfer step. But when you say E1 and E2, the only thing I can think about is
like an EE reaction, I guess.
Like E1, E2 is from organic chemistry. Or maybe you are talking about like an EE, a double electron transfer.
That's what I thought. I mean, I could be wrong. It seems to me, Barry, like you're asking, how do you know the difference if you have an electrochemical and then a chemical step, or 2 electrochemical steps in a row? And maybe you're thinking something different. That's what I thought he was asking. You might be right. I don't know terminology wise if he says something different.
So Barry, please clarify what you mean by E1 and E2. Otherwise, I'm going to just take you to a page of organic chemistry.
He says correct. I think I'm assuming
correct.
We both said stuff.
We both said stuff.
I think you mean it's electrochemistry and like an electrochemical.
Oh, EE, double electron transfer.
Okay.
Oh,
yeah. So it's what I said. I think is the correct.
I'm like, I'm trying to look at some organic chemistry stuff and all those types of things.
I think this is a good opportunity for you to show sim stuff.
Yes, that's what I am going to do. So can everybody see? Yeah.
Okay.
So Barry and everybody, this is Aftermath Live. Actually, this is our simulation software. So if I'm doing, so what you can do with this software is you can actually simulate these very mechanisms that you're talking about, and we can talk a little bit about what are the characteristics associated with it. So if I just have a regular, so just to show you, if I just have a simple electron transfer reaction, I can automatically fill this stuff up and then simulate, and I can get a cyclovoltammogram. I can look at the surface concentration as a function of time, as well as the concentration, the diffusion concentration profile, as a function of time. Now, the mechanisms that you're referring to specifically, they are going to be different, and they are in this template, so to say. So let's talk about an EC reaction. So this is an electron transfer followed by a chemical step. Again, I can kind of autofill these to show you, but all right, my electron transfer is here. It's at 0 volts. And then this is the kind of the rate reaction. It's, so A plus an electron goes to B, and then B is in equilibrium with C. So this is my chemical reaction, and I can adjust the forward and reverse rates. I can make this very fast, effectively adjusting the equilibrium constant. If I simulate it, you'll notice that this is for that the oxidized, and actually let's make it a little bit more pronounced. Let's say the forward rate, most of B goes to C. As you simulate it, you'll end up getting a lot more. You'll get less, you reduce it, and then you'll get a lot less of the oxidized form of B going back to A on the reverse sweep. Now, there are a couple things for analysis associated with this type of reaction. One thing you can do is you can actually start to change the concentration of these species and notice any kind of difference. That's one tool that you have. But one thing that's a little bit easier to do is change the sweep rate. So let's say this is slow. Sorry. Let's say this is 10 millivolts per second. If I simulate this, you actually end up getting a little bit, fairly consistent, which actually I wasn't exactly anticipating. Oh yeah, no, you get less current here, and I think less current here. I'll have to open up, but my thought is if you actually scan more quickly, you end up. This is actually not what I would anticipate because
the peak is growing because of the scan rate, but
no, this is because if you're sweeping the voltage fast enough, there will not be as much time for this reaction to go. So in principle, as you scan faster, you should observe that it actually looks more like a normal voltammogram. That's normally what you would observe for like an EC reaction. So unless, let's see if I make this faster. Yeah, then you see mirror. That makes sense. So this is fine. It may be the case that I have it such that this is again something I have to kind of play with. But yeah, if you make the reaction, so actually if I make the reaction very slow, so let's see, if this goes back, if I end up getting more B, then it looks more like a normal voltammogram. But adjusting the sweep rate is the thing that ultimately will be what you can really play with. Now, if you were doing something like a CE reaction, this is the case where you have the chemical step first, and then you have the reduction reaction. So again, let me autofill this, and if we simulate this, you'll probably get something like this. And again, what we can do, what you can at least do, and what some people have done, is usually this kind of reaction in some cases is maybe it's like an acid catalyzed reaction. So what a lot of people do is they'll change basically the equilibrium, sort of say the rate constants using stronger acids with say stronger or lower pKa's to actually get this reaction to be something like this. And when they do that, you'll end up getting these kinds of different results as you change the acid, not concentration, but activity. So, and additionally, yes, you can also adjust the concentration of the acid that you're using. So if I have like 10 millimolar, you will mostly not see a major difference in terms of how it'll look or behave. But usually changing the acid or the how quick this reaction occurs will affect how this reaction will occur. So this is all to say, for the most part, that using this simulation software is probably one of the best ways to kind of model your system to determine whether you have like an EC or a CE reaction. And lastly, I'll go to like a double electron transfer. Most of the time, two electron transfers will occur one after another. It's rarely the case that you'll have a sequential electron transfer where two electrons actually occur one on top of another. It'll usually be one, and then some time will pass. Maybe this is something like 400 or something. There'll actually be a bigger peak separation between like one redox pair and another redox pair. It's rare that both of them will be in just one big voltammogram. So that's how I would observe a two electron versus EC and the CE type of mechanism. Let's see. Has there been hopefully that was helpful. But yeah. Feel free to ask any other questions. Also, if you want to, you can go to aftermathlive.com to actually check out the software and play with it. And you'll probably use a more up-to-date version of the software than the one I'm using. All right. Moving forward, we have a question from Dirija, I think, maybe. Sorry.
Dareed?
Dareed. We're gonna try our best to pronounce names, but I make no promises. Hi, in my curve of CV, the current is increasing, and there's not a I think that's supposed to be peak
Yep.
of oxidation, and just a peak of reduction. Please, how I interpret this result?
I'll take this one.
Yeah.
So
want to.
my ability to answer will be limited simply because I'm not looking at your
Yeah.
data, right? But what I'll share with you is a possibility that I can maybe guess based on something that is plausible. Let me just put it that way. So if I have a CV, for example, and I have something like I scan positive and I get a positive increase in the current, and then when I scan back, I get a reduction peak. But I don't have per se any oxidation peak. What it might mean, for example, is that my oxidation peak is in here. In other words, I am scanning very positively, probably to the extent that I have the oxygen evolution reaction, right? If I'm assuming, and I'm making a lot of assumptions here. So let's say whatever I have for a system, my electrode, my redox species, whatever it is, that it, you might expect to see a peak here or something, but you don't. And so you don't get that oxidation current until you start scanning more positively. That's an indication potentially of a poor electrocatalyst because it has a very high overpotential required to oxidize something. And so the ideal situation is I would have a peak right here, but instead I end up oxidizing whatever the thing is that I'm trying to oxidize. This right here might be, whatever, 600 millivolts, right? And then instead it takes until 1 volt to oxidize. So it's like I have a high over potential. My catalyst isn't doing a very good job, whatever. So the reality is that the coupling peak won't resolve because I have to go much more positive, and then by that point I'm already at the limit of my electrolyte, which is in this case aqueous. Assuming water, you're at the limit of your electrolyte stability, and you're just going to keep ripping oxygen out in the oxygen evolution reaction. Sometimes if you scan positively, sometimes if you scan like fast enough, you can kind of get a peak out of it, like on its way towards more oxygen evolution. It's a little bit of a difficult kind of a thing to do, but that might be what you have, is that the oxidation is just coupled, like convoluted within something else, like the oxygen evolution reaction. And then when you scan backwards, you get the reduction peak, that because you oxidize something, and so there is something to reduce. It's just far more positive potential than you would like to have, for clarity in viewing. That's my guess as to what you're seeing and for why. But again, without maybe seeing your data and knowing specifics of your system, I probably can't answer more specifically than that, but maybe consider those things if that is accurate for what you're seeing.
Okay. Yep. No, I think that's a great answer. I've seen peaks and stuff just like that, and it's like, yeah, sometimes you have to sweep a little bit further, and you can see something. But I think that's good. Hello. What are the most important things to consider if I'm attempting to grow single crystals via electrocrystallization, aside from materials purity? Thanks. Well, Asbinge, I have zero experience with growing single crystals via electrocrystallization. I don't even know what electrocrystallization is. So I would have to say I don't know the answer.
I don't know with definitive answers either. What I will say is that my guess, based on some experience, I suppose, with similar kinds of experiments, is that if you're trying to grow like really specific crystal faces and things like that, you're probably looking at very, very slow rates, which means probably really low current. There's a lot here, right? It's like you have to determine procedurally is this the kind of thing that requires a constant rate, which would be current, right? So you would say, okay, well, if I, and you're trying to grow like single crystal, so that's usually like one specific crystal face. If you have a too high of a current, too much passivation layer, too much other stuff, you might convolute it. It might cause a polycrystalline formation, and that would be bad. So you might, and this is like the answer to these sort of things that I'm saying might be just in the literature. Like I don't know, right? But it might be that like, okay, well, if I have a rate of, microamp per centimeter squared, right? Or whatever, like that's the current you need to have. So what you want to do is like a chronopotentiometry experiment with a very low controlled rate. Now, on the other hand, it might be just the opposite, right? Which is to say, if I have a potential above whatever, I start getting polycrystalline facets or something. Whereas if the potential is between whatever range, that's the desired potential that will form a crystal that I need. So I'm just throwing all these out there to say, a lot of the answer is probably buried in literature and what or thermodynamics, frankly, about what rates / potentials are really required. Because there are, for example, metals, transition metals and things like that have a lot of different oxidation states and a lot of potentials associated with different processes. And it's like you might have to be like, well, if I'm at 300 millivolts, it'll do this one, but if I go up to 400, the 2 electron step will happen, but here the one. So it's like I need to be greater than 300 but less than 400. Like that might be the case for you, and if that is the case, it might be tougher to do chronopotentiometry because you're not controlling the potential. So that's the first thing, is that you might have to just figure out what method is critical, whether the potential is critical for formation of a particular crystal face or the rate, because you can't control both, right? You're either going to have a set rate of formation, which is the current, a flat rate of charge is associated with a certain number of moles per second per whatever, and then the potential will be whatever it's going to be. Or again, you're picking that potential to drive thermodynamically whatever specific reaction of interest, but your current will be whatever it's going to be. And so if you want to, you'll have a charge you can integrate under the curve, and it's not going to be exactly the same throughout. So you have to figure out which one of those it is. The only other thing that I'll say in this regard is that sometimes the answer for like growing crystals and or just growing or electrodeposition and things of that nature is our electrolyte additives. So there are different kinds of processes. And I can only say very generally about this because I don't know a lot of specifics, and I also don't know specifically what system you're using, nor do I probably know the details of that system if you were to tell me, to be honest. That being said, there are ways, for example, that people modify the electrolyte to add things like an accelerant or a decelerant to speed up or slow down the rate of crystal growth. And so you might need to figure out again kind of what composition of your electrolyte is most conducive for the rate of growth that you want, right? I think that's the most that I can really say about for your questions. Anything more and it's probably beyond my understanding, to be honest. So I hope that's at least a little bit of snippets that might maybe guide you in the right direction.
Mm-hmm. All right. Nikos asks, hello, congrats on your work. Hope for the best. I just want to ask what conclusions can be obtained from a CV graph for a battery. Also from EIS, what information can be extracted? Thank you. I know that you are the battery
There's a
expert.
question about batteries. I was looking at things.
Yeah, I know. Yeah, it's a question about batteries.
Yeah, I was looking for another question. So let me
No.
Let me actually pay attention for now. Conclusions can be obtained from a CV graph for a battery. Also from EIS, what info? Yeah. Okay. So generally speaking, you don't do CV on a battery. Not not very often. I do get this question sometimes. I think the best way that I've found to answer it is that a cyclic voltammogram is a set rate of change of voltage, right? You're sweeping the voltage from somewhere to somewhere. You get a resulting current, right, from that, okay? So the first thing is that, without getting down a forever rabbit hole of battery discussion for the next 2 hours, batteries, often capacitors as well, are typically devices that are better suited for constant, just like I was talking about before, actually, it's a constant rate of charge or discharge, which is current. The rate of charge and discharge is related to the current. So this is often why battery experiments involve constant current for some period of time. So that's the first thing. So the first thing is that very often you do not want to sweep potential or control potential, because you will have an irregular or asymmetric rate of charge or discharge. So that's the first thing. So very often you don't do cyclic voltammetry. This, another reason, I suppose, or maybe what I would say is the second reason of the two I'm going to share with you, why cyclic voltammetry is not often used in a battery, is that people often do cyclic voltammetry and think about CV with an aqueous system. You sort of scan back and forth, let's say 50 millivolts a second, 100 millivolts a second. You go throughout the whole voltage range, right? Even if you have a volt of range, like 0 to 1 at 100 millivolts per second, it takes you 10 seconds to scan from 0 to 1. 10 seconds going throughout the whole voltage range of a battery is really fast. Batteries are not meant to be charged and discharged in 10 seconds, right? I mean, think about it. Think about your phone, charging it. You wake up in the morning, you unplug it, and in 10 seconds, it's dead, right? Or you plug it in, and 10 seconds later, your phone is gone from 0 to 100. Like, that's not reality, right? Even the fast charging phones that we have now and whatever, it's like, it still takes like 40 minutes or something. I'm just trying to prep you on the thinking about it from a time perspective. So cyclic voltammetry is observing the transient current response over the voltage range. Well, in a battery, you are spanning the voltage range, if you're doing a cyclic voltammogram, most of the time between over its whole range of charge, charge discharge characteristics. And so what that entails is, effectively, unless your scan rate is really slow, which people typically do if they do CV at all on a battery, and I'm talking like 0.1 millivolts per second, you're gonna just charge or discharge your battery way too quickly. Okay, so those are the reasons why CV is not typically done on a battery. However, I will say that the answer to your question, for the most part, what can be obtained from a CV graph of a battery, basically, if you do a CV within the parameters I just described, what you get from it is the same thing you get from a CV of anything else. You get the transient current behavior, you get the position of, peaks corresponding to a Faradaic process, right? Which is probably the charge discharge, intercalation, deintercalation, SEI formation. You'll get, if you scan really slowly and you go the length of the voltage range that you have, you'll get the characteristic behavior. But it's tricky because you're not charging or discharging at a set rate. So it's not typically used for analysis purposes about how well the battery is performing or things like that. And then the second part of your question, what do you get from EIS? All of the same kinds of stuff. You get information about the intercalation, deintercalation, charge, discharge, whatever. But, very specifically, impedance will give you things like, especially if you do impedance over a period of time or a set of states of charge of your battery, you'll get things like the change in the internal resistance of the battery, change in the charge transfer resistance of either or both the anode and the cathode processes. You can get a measure in the change of the SEI charge transfer resistance, which can be I think in some ways either directly or at least loosely correlated to the SEI thickness, which can be a critical parameter for determining how healthy your battery is essentially. And then, of course, the measure of the capacitance of your battery, of either or both the anode and the cathode, diffusional properties, a lot of the same sorts of things that, and EIS in general gives you from analysis purposes. Those are the kinds of things that people are often looking at with batteries. And again, it's typically done to track those properties as they change with respect to either time, state of charge, or number of cycles, which is sort of a time, right? It's like, oh, after every 500 cycles, how's my battery doing? Something like that.
All right, very good. There was a question from Gangster228.
Yeah, I wanted to show that.
Oh, okay.
So I just pulled up our current, for example, the first question to you
Mhm.
is about what version you're using. So the first thing I'll say is that check out our website here, right? So I'm sharing the screen. I'm going to
Mhm.
link it. I'll put the link. Did you put the link yet, or
Well, I actually gave him a link just to
to our
ask us a
email?
question so
Sure.
that he could
Yeah, you could.
elaborate on the problem that he's observing.
Yeah. So if you want to email us if you're having some problems with the software, please go ahead and do so. I just wanted to show you that the current version of our software is available on this website right here. I just put the link. This downloads it 1.6.105.23. Okay. So that's the first thing.
Mhm.
If you don't have that version, I suggest upgrading to that version. And then the second thing is that I think it's working. You put the Savitzky-Golay or something like
Yeah.
that, that particular method. So for example, I just have a random, this is
Mhm.
EIS data. Forget about, it doesn't even really matter what the data is. I just want to show you to my eyes, it appears to be working. So for example, if I apply a smoothing transform, it actually defaults to the Savitzky-Golay smoothing. And I'm not messing with any of the parameters. So maybe you have parameters. It's possible that if you pick,
Is that a pop-up that's coming
oh,
up?
is it not showing? Yeah, I'm
Yeah.
sorry. It's not showing. Let me share like,
Yeah, no, I know it can be a
yes, shoot, it's
little
not
annoying.
showing. That's always a thing. Thank you for mentioning that.
Yeah, I was
I
just
always
like,
do that.
he's just moving a thing
Yep,
around.
I'm
a
just
little-
moving, showing nothing. I think the pop-up is a separate thing. So here, I'm just
Yeah.
showing the pop-up. It's probably a bit odd.
Yeah.
People
No,
are
here we
figuring
go.
out. So
Actually,
this
it
is the
looks good.
pop-up that comes, right? The Savitzky-Golay.
Mhm.
So now the first thing is that you might, I don't know, right? You might have some of these, I don't know, parameters adjusted. I think it's possible that if you like mess with these different parameters, it might not work for one mathematical reason or another. I can't speak more clearly to like the algorithm, like, oh, well, you have to have, half width window has to be something in polynomial order. It could be, like, I think if you have too high of a polynomial order, it might give you an error anyway. So that's the first thing. The second is that just generally, right, with default settings, I know I'll go back and share. Okay, back to the software proper. If I just shared the screen, it would be fine, but I don't want to share the screen because now we'll be like Inception ourselves. You know what I mean?
Yeah.
So anyway, I just did it. You can see that it just applied it. This is the result. So anyway, I'm not seeing that problem on our current version. So just like Alex said, if you are having an issue, please email us. We can try to get to the bottom of it. My other advice is try downloading the most recent version. It appears that it's working. I don't see an error here.
Mhm.
So possibly it's a version thing. Possibly it's some of the parameters you're picking. And if not, if there's still issues, we'll certainly help you get to the bottom of it.
Okay. Yeah. Thank you, Gangster. All right, from Alex, not me, someone else. Hi, I have thin films that conduct E well and OH poorly. I can apply them to an ionic membrane or between two membranes, carbon paper, or maybe on an insulator. How can I measure pure ionic conductivity? Thanks. So, my understanding, or somewhat limited understanding, is you want to basically measure the conductivity of your thin film. I would use there are these membrane cells, and we offer these membrane cells. So you'd use such a membrane cell, and let me actually pull one up, so that you at least have a general idea about what we're, or at least what I'm talking about. So I think this one at least kind of visually will show. So let me just go back and share screen. And then, okay. Yeah. So this would be the cell that you would use. This is one of our advanced membrane cells. So there's two cells. Your membrane would be here, and then you would put electrodes on either side. So in some ionic conductivity experiments, they might just put two platinum electrodes. You want something that's conductive on both sides, or at least very conductive on both sides. And then you would actually do impedance to get the resistance. And then 1 over the resistance would give you the conductivity. And impedance actually gives you a much better description because it's a frequency-based resistance or a frequency-based impedance. So that would be the way you would determine the impedance, and then you take 1 over that to actually get what the conductivity is. That is a way you can measure the conductivity for your membrane. And so you'd have to pick, whichever electrolyte. It'll depend on the electrolyte and the composition, but generally speaking, that is what you would do to calculate your conductivity. Hopefully that was helpful. If you need further clarification, please let us know.
I think the thing that's hard about this question actually is
about measuring conductivity.
Well, it's ionic conductivity or
electrical conductivity.
Yeah, or no, yeah, right, exactly.
Oh, okay.
And I guess
purely
so.
ionic
Ionic conductivity is what you described. It's like it's the conductivity through a membrane, right? And you can do that with the cell you described, or we have a variant of that has Lugan capillaries, where you do like a 4-point probe, and it's a similar kind of a thing. But I almost think Alex, not you, Alex.
Yeah,
there's Alex.
Alex.
I wonder what kind of conductivity you're asking about, because you said that your thin film conducts electricity well, but hydroxide poorly. So I guess again, it's like, are you trying to measure? Maybe you are trying to measure the hydroxide ion conductivity because it's poor. So you want to know like what it is, how poor is it, whatever, what the number is. Because this is actually a tricky thing. I don't actually know how people measure electronic conductivity. I don't think that's an electrochemical. Can that be done electrochemically? Because the ionic conductivity is like what you said. It's like through a membrane kind of a thing.
Yeah, it's through a membrane. I think.
But if it's electronic conductivity,
so if it's electron, so first off, there needs to be electron transfer between it, and you may even use something like two metals literally pushed together, and then see how well does that conduct electricity, like electron transfer.
Yeah.
That would be the way I would think about it, from a electron conductivity type of standpoint. And you'll get something different, when you put two dissimilar metals together. They form some kind of interface, and there's a break in between the two metals, so you're going to see some kind of interface. And when you put a membrane between them, you'll get something. You'll learn a little bit more about the conductivity. But as long as there's no Faradaic reactions occurring, I think that's another point. As long as you are doing EIS at a potential where no electron transfer reactions are occurring on the platinum or whatever your two electrodes are, then you should just be measuring ionic conductivity.
Yeah, I think that's true. I think that the electronic conductivity thing always confuses me as far as measurement. It doesn't. It's like anyway, it's not really an electrochemistry thing as much. Like,
well, it would be like solid electron transfer type of things.
But it's just like the common, you know what I mean? Like 3 electrode, whatever.
Yes.
It's like we often take for granted, even if we're using like a semiconductor, that it's electrically conductive. Like it is just like platinum or copper. Like it's just electrically conductive. Like we don't think about it.
Yeah. Yes.
Right. So electrical conductivity is kind of like, in our world, I always find it to be something that's just taken for granted for the most
Oh
part.
yeah,
you know?
yeah, absolutely, absolutely.
I don't often think about its measurement or its or anything like that.
Yeah,
Yeah. Anyway,
yeah, no,
it's a
absolutely.
bit of an aside, I guess, but yeah, that is one of those things. 4-point probe for electric. Yeah, I think that is a possibility. And again, the tricky thing is, and people often get confused about this, and I often have to get my mind right about it. Fat Cato has a
Yeah.
comment about that. The 4-point probe is a conductivity measurement thing. It's just that you have to get your mind right about whether you mean electronic conductivity or ionic conductivity. You know what I mean? Like membrane conductivity. Those, because
Yeah.
they are different things. Obviously, if your membrane is electrically conductive, it's a poor membrane in a lot of cases. It's like
Oh, it's
you'll
not
short.
actually.
It's like if you have
Yeah,
anode
actually shorts.
cathode on either side of a membrane, it can't be electrically conducting, or you'll just short the whole cell and it's irrelevant. So
Yeah,
it has to conduct ions and not electrons in a lot of cases.
yeah.
Anyway, I'm sorry, I'm kind of
No, it's fine. It is
talking about this, but it's just one of those things that I like to try to keep my head on straight about, which I
Oh, yeah.
apparently can't do. So
No. It is tricky. It's
Yeah.
definitely tricky. This is a follow-up from Deirdre. I'm just gonna say, apologize for mispronouncing the name. This has to do about applying a voltage and doing cyclovoltammetry, getting a voltage for oxidation, and then getting a peak for reduction, but there's no peak for the oxidation. And so, as a follow-up, she's saying I changed the scan rate 5 to 100 millivolts per second. What the effect of the rate? I know when I increase the rate, the current increases, but I know, but how do I know? I guess it's how do I know the limit of the scan rate? So this is a good question. So just to reiterate a little bit about our previous answer, one thing that's very helpful is there's changing the scan rate, which is just easier to kind of show it here. So in cyclovoltammetry, if I am applying, if this is my waveform, this is time, and this is voltage. There is, so you can have, there's this rate, sort of say, and this is the scan rate. It's the slope. It's the slope of this voltage versus time curve. If you have faster scan rates, you have a kind of a steeper slope, actually, because you want to apply it to the same potential. So you can reach, sometimes you can reach points faster, right, in time if the slope is steeper. So that's just that's just scan rate. But what I was recommending initially was that when you're looking at your current versus voltage, you actually increase where you go, what this voltage is. You may be going here, but going here may actually show that there is a little peak that's there, such that when you go back, you do see this reverse wave. So there's the potential window, which is this, and then there's the scan rate, which is this guy. So what the scan rate does, in many ways, it changes a few things, and you can think about it. One of the most important things that you can gauge from it is a little bit of the speed of the kinetics that are happening. But what typically happens is the current increases, but that current is a background current. That current is typically associated with double layer charging. So the best way I have to kind of describe that is, if you have the electrode surface, let's just say this whole thing is the surface. Over time, if you're like doing an oxidation, you have plus charge at the surface, and then you'll attract negatively charged anions here, and that's charging. You'll have electrical double layer charging, and you'll have electrical double layer charging with that's actually an arrow. And the current associated with that is this. And I don't know if I'm blocking, if this is able to be seen. Let's make sure that the
I moved the
you
question.
moved the
You're
question.
good. Yeah. Sorry,
Okay.
I did it at the beginning. I figured you need the room.
Okay, thank you. So as you this change in voltage as change in time is your scan rate. So that's the scan rate. So your background double layer charging current is will increase or decrease depending on the scan rate. So that's one of the most obvious things. That's the thing that I believe you are observing right now is you're seeing an increase in this background current, mostly associated with the scan rate. There's another process. If you did have a peak in a traditional cyclic voltammogram, so let me just kind of erase this. Let's say you did have a peak. Use the lasso tool here. So if you did have a peak in a more traditional diffusion controlled cyclic voltammogram, the peak current will also change as a function of the square root of the scan rate. It's proportional to the current. And that's known as what's called the Randall's-Savitzky equation. So changing the scan rate is a way of kind of extrapolating between these two things and helps you observe things. So hopefully that's kind of a quick answer about scan rate. It's also a way if you had things like if you had an electron transfer followed by a chemical step, you could maybe sweep the potential fast enough such that the chemical step either doesn't occur. That is one thing that you can do. There's a lot that you can do with regards to the scan rate when it comes to interpreting your cyclic voltammetry data.
I think the other thing I would add to that is simply that if you're asking the last part of the question was, what is the limit of the scan rate? Technically there isn't one. The practical limit for like how fast you can scan 100, 200, 300, 500 millivolts per second. Like, you know what I mean? Like you can just keep scanning faster and you'll see the phenomenon Alex was just talking about, which is that, you know, the background current will grow. If you have peaks, they'll grow based on the Randall-Savitzky equation. You know, in theory, forever, right? Practically, your limit is going to be probably determined by your potentiostat.
Yeah.
The limit for how fast you can actually scan is going to be determined by the capabilities of the instrument you're using, how fast it can actually physically scan, and how well it can resolve data at that speed. Like those, you know, those are just like
practical limits.
Yeah, practical hardware limitations. Like, you know, in theory, the answer is there is no limit. You could scan at 1 billion volts a second.
Yes.
And in theory, you know, practically it probably wouldn't happen. There'd be other crazy things happening. But you know, in theory, you can scan faster and faster, and these relationships will hold true, right? I mean, again, in theory,
probably, they'll break apart at some point.
Yeah, at some point, we'll get some
within the limits here.
Probably for CV, if I have to give you a number to try to give you a solution here, probably like somewhere between 250 and 500 millivolts per second is like as fast as you're going to want to go. Like for the most part, in most normal CV experiments, like you don't see a lot of people scanning faster than like 250 millivolts per second, something like that, right? Beyond that, you start getting to things like fast scan cyclic voltammetry, which is used in like neurological kinds of data, and that's a whole different ball of wax. I'm not getting into that.
Yeah.
So practically, I wouldn't really suggest scanning much faster than that. Just if nothing else, for comparison with what other folks are doing. That's what I would suggest.
Yeah.
Ayub has a question. It says, can we break the covalent bond in a molecule? It looks like you have a nice altruistic sort of idea here. If you can break the CO2 bond and make smoke from cars not dangerous. So it's a nice thought. So first of all, you can break the bonds in CO2, like CO2 reduction, for example, electrochemically is a big field of research, right? I mean, millions, and I shouldn't say millions, thousands. There aren't millions of electrochemists.
Not millions of
our field is unfortunately not full of millions and millions of people. Anyway, lots and lots of people are doing research on CO2 reduction because CO2 can be reduced. Now, fundamentally and chemically, it is quite difficult to, or can be, I should say, it can be difficult to break. You know, the more like a CO2 has what, it's 2 double bonds, right? 2 double bonded C and oxygen.
Yeah. So it'll have 2 double bonds. Yeah. So there's a double bond to one oxygen. There's a double bond to the other oxygen.
Right. So like just sort of in general, it's like a little bit more fundamentally energy intensive to break a double bond than a single bond, and a triple bond than a double, like, so there's something to that if you want to go there, I suppose. But yeah, of course you can, CO2 can be at least electrochemically, right? Reduced and transformed into other things. CO2 can be dissolved into water and it forms carbonic acid effectively. So anyway, CO2 can be transformed. It's not an impossibility by any stretch of the imagination. And the only other brief thing I'll say here is that you have very good, I don't know, well-meaning, probably, you're trying to make cars cleaner and stuff like that, right? But what I would say to you is that for the most part, the reason that cars are spitting out ugly smoke, if you live somewhere perhaps where there's a lot of vehicles that are dirty exhaust and things like that, or just anywhere you see that's not CO2.
Yeah, that's also true.
CO2 is odorless and colorless. So if you're seeing a lot of smoke coming out of the tailpipe of a vehicle, that's not carbon dioxide, my friend. I'm very sorry. It's a lot of other stuff. It's a bit much to get into, but that's a combination of incomplete combustion, other toxic kinds of materials, improperly dirty fuels often produce stuff like that. Sometimes it's other compounds like sulfur compounds, coal or hydrocarbons and petrochemicals that aren't properly scrubbed and cleaned will have other contaminants in them, and those will at times cause odor and smoke to come out. So those are some of the things. A car that's burning extraordinarily cleanly will not have practically any odor or color coming out of its tailpipe.
Yeah.
So I like where you're thinking, and you certainly seem to be wanting to solve some real world problems, which is, you should be commended for that. But fundamentally, smoke out of cars is not really a CO2 problem.
Also, another thing is if you do reduce CO2, you can form CO, and CO is actually
much more
dangerous
toxic,
than CO2. So it's a complicated problem.
It is a complicated problem, to say the very least, right? But I think in general, I appreciate folks who are thinking along these lines, right? Trying to solve real world problems, and it's I appreciate that just in general. So good for you, I suppose, is what I mean that genuinely. Anyway,
Fat Cato has a question.
That's right.
It's a great name.
I can pronounce it too. It's excellent.
Yeah.
So it says, hi guys, when Warburg area in EIS is curved downward but doesn't touch the x-axis, is it still considered a finite Warburg? Yes, it can be. Let me show you an example. So I have a circuit here. I know it's small, and I'm not going to do the circuit thing because it puts a pop-up and then it won't show because I'm like sharing this window and it's a different window. Effectively, the circuit I'm drawing here is a one variant where there's a finite Warburg, right? So I have like a Randall's element and then a finite Warburg. The situation you're talking about is probably something like this. Try to get it in screen. You know what I mean? So it's entirely possible, and this is just one specific example, right? This is not touching the x-axis, but it's clearly a shorted finite Warburg element in this case, right? I have a sort of a 45 degrees diffusional tail starting, and then it starts to curl. It's the same explanation that you can have a semicircle that doesn't totally reach the x-axis, and it still means that you have a Randall's element or a charge transfer process. It just means one of two things. It means that the value of, in that case, the Randall's element, it means the value of the capacitor is such, usually quite large, that you have to go to lower frequencies to resolve it, and maybe you didn't for whatever reason, right? So for example, I can lower the frequency here and it will probably touch the ground, touch the x-axis. See, so it's like the answer. Now this is a simulation. It's easy to do that. In practical world, you don't usually go to 1 millihertz because it takes absolutely forever and it's annoying. So you might not be able to go to lower frequencies to get it to touch the x-axis, but you don't have to. In fact, for most fitting algorithms, it can fit the data even if it doesn't fully resolve, so to speak. And it certainly doesn't mean that I don't have a finite Warburg element. Now, of course, there are limits to this. For example, if I really, let me zoom out so you start to see. If I really start to play with these parameters, you can see that eventually it's like, well, if it's curling like this, is it really a finite? Like, definitely finite Warburg. Definitely not. Maybe it is. Maybe it's. There's a transitional. There's a certain values of it where it. You might say something like the finite length is finite, but it's really big. It's almost infinite. There's a, obviously, as you can see here, technically a sliding scale for that W. You can see how it's impacting the curl. So the answer to your question directly is no, for sure. It could still be one, but there's a gray area here where the length of your diffusion layer grows to can grow so much to the effect that it's practically infinite. So take that for what it's worth, I suppose.
All right. Bilal has I have a two-part question. To determine the deposition potential to reduce a material on another, the cathodic scan sometimes shows the reduction peak that define the deposition potential, but not always the case. Why? And then as a follow-up, I mean, it is not necessary to define the reduction potential based on the existence of reduction peak. So I'm going to what I think is happening, Bilal, is you're doing either an over or an under potential deposition. So you are using you have two dissimilar metals, and so one of them is your electrode, and then you have another material that's dissolved. Let's say maybe it's like copper in the 2+ or iron in the 2+ oxidation state, and you're reducing it cathodically on the surface, and it's under potential deposition. So if you are now, when you're doing something like an over or an under potential deposition, it only works for when you get that first layer, right? You're reducing one molecule or one metal onto another, and there's a potential associated with that reduction. But the next time another metal is approaching the surface, another iron or another copper or something is approaching the surface, there's no more of that base metal or that base material that's available. So you're unable to deposit any additional metal. You don't see a current, and hence your peak goes away. So that is what I think you are talking about. Please leave a comment to let me know, or to let Neil and I know if that seems to be the case. If you are trying to do this two dissimilar metals and plate one on the other, because that would be a reason why you sometimes only see the reduction potential. That is one hypothesis, at least, about what I think might be happening. But I do believe that to define a reduction potential, you will need to have a peak. Like, you will need to have some kind of reduction peak. So the experiment that you may need to do is, after you do the deposition and maybe you don't get any peak data or something, you might need to polish or clean the electrode, maybe pre-treat it so that that layer is no longer on the electrode surface. And then when you put it back into your electrochemical cell, you make sure you're at, say, a very positive potential to make sure that no reduction occurs. And then as you sweep the potential, you should see a peak associated with the reduction of that metal cathodically onto the other metal that you have. That's what I think. That's my hypothesis, at least. So without knowing any more details on your system.
Sounds reasonable to me.
Very good.
And
yeah, Fat Cato has I don't know if this is a response for something else. He says, I thought CV is to see the redox peaks. You can certainly see redox peaks using CV. CV can be used probably for a bunch of different things, but generally speaking, yes. CV can be used to observe redox peaks and other electrochemical processes that might be occurring within your electrochemical system. But it's kind of all-purpose electrochemical technique, sort of say.
All purpose.
Yeah, we got a question from Race.
Good to
Race.
see you
Yeah,
again,
good to see you
Race.
again, Race. So it says, hi guys. Could you please know what's meant by drift correction? Thanks. I believe what drift, and I guess I'd have to do a search to really know for sure, but my assumption is that the reference electrode in an electrochemical system, the potential might be drifting. It's no longer.
Or it's an EIS thing.
Oh, or it's an
Actually, yeah.
EIS thing?
So there's a
Oh,
distinct
there's an EIS drift.
there's a
Yeah, that's
distinct
right.
thing with EIS that's called drift correction that I can explain and draw.
Yeah.
Race, can you please clarify what you mean? Can actually before
Yeah.
before
we
you go down a path
Yeah.
of reference electrode
shit.
correction and I go down a path of impedance correction.
Yeah, that's right.
I want to know which one you mean.
Yes.
So please clarify, and then one of us will drone on and give you an answer.
Yes.
Before we go down one of the roads that is not what you're asking about, because there's a couple of different ways that you could mean drift correction. So please clarify. We'll move on to another question before.
Yeah. And then
there are a couple of different things that sort of fall under the explanation of drift correction. I want to be clear what you're asking.
yes.
Gangster, this is just another bit thing here. So you say when you're taking the derivative of smooth graphs and you say used for CVA, you clarified CVA, not CV. I don't know what that is, to be honest.
Yeah.
But you see periodic sharp peaks are visible. So again, I'll just share with you. I was just looking at this again because I'm trying to see if I can recreate any issues. And as you can see, I'm just kind of messing with some data I happen to have. So I'm just making a fresh plot. I'm just doing. I know you won't see the pop out. You know what I mean? But I'll just try to illustrate what I'm seeing, and I don't think I'm seeing the same thing. So again, you can't see the thing, but I'm doing the smoothing. So that's the smooth data, right? And now I'm doing a differentiation. Okay, I know you can't see the pop out, but I'm just gonna do a differentiation for a first order, and
okay.
So the other thing, the first thing I'll say about this is that this isn't necessarily wrong. This. Let me see.
I mean, we may have to look into this.
This
right?
is. I don't know that there's anything wrong. I think that again, this. I also think that this might be a bad example because it's logarithmic scale and it's exacerbating some of the things here. I guess the point is that I'm not convinced that what I'm seeing is necessarily wrong. That's all. I'll just do another one and kind of see here because I'm not sure that this is incorrect. Again, this is just doing mathematical derivation, and there are changes to these. Like if I zoomed in on some of these, I don't know that it's all incorrect, and also the scale of it is not necessarily is not maybe so great that anyway. I'm not convinced this is wrong. Now, if it might be the case that it is, for example, if you are doing it manually, and you say, oh, this is definitely not what that derivative is, or something like that, then we can certainly look into that. But yeah, like I said, give me give us an email if you want. We can try to look into this some more. But I'm not 100% convinced that this is a problem. And for sure, the smoothing seems to work on the current version. So I just wanted to kind of touch on that. And then Gangster had this point here. So yeah, so I suppose I can get into this now.
we can.
I see there are a lot of other questions.
Yeah,
we're going to try to get to you as
them.
quickly as we can, everybody. Thank you for the questions. And
stay tuned. We will get to your questions.
We're answering as fast as we can. So there was a question that Gangster actually had on as a comment on one of our YouTube channels, YouTube videos, basically. And it was something to the effect of, why does the impedance of the reference electrode affect the results, especially if no current passes through it? And so this was in relation to a video that I made describing how a shunt works. Okay. And so I'm not going to get into how a shunt works. We have a video for that. I don't want to spend for a really long time going over that. I encourage you to check out our channel. Maybe you can put the link to it, Alex, or something like that. If you want.
I can find it.
But effectively, the first thing that I said in Gangster, again, apologies that I think I misled you into a line of thinking that isn't helpful. I just was trying to make a logistical, technical point, which is that it is not true that no current passes through the reference electrode. A very small amount of current does. But I don't want to belabor that point because it isn't really relevant. Like, it's just, I shouldn't say it isn't relevant. It's technically true. I just wanted to be complete, so to just for the sake of completion, right? Technically, current does pass from the potentiostat through the reference electrode. Otherwise, it wouldn't work. That being said, that amount of current does not impact the reference potential. It does not impact the reference electrode. It does not affect the, like, AgCl, calomel, whatever, like, couple. It doesn't affect its potential. It doesn't do any of that. Okay. The reason specifically why, in particular EIS, the impedance of a reference electrode affects results, especially at high frequency, is because of stray capacitance, basically. Let me draw this for you and I'll show you the calculations. So a reference electrode typically looks something like this, right? I'm not drawing the whole thing from the top to the bottom, but I'm going to draw a little bit of it, okay? And it's in electrolyte. And I have a frit down here. Okay. Now, this right here, let's say this is the reference couple. This is AgCl, right? This is the electrolyte. This is the reference electrode itself. Now, the normal situation that a potentiostat is doing is it is measuring the potential of this, right? This is about, whatever, some standard potential, 200 millivolts. It's whatever it is, 190, whatever. Depends on the KCl concentration inside. All of that is kind of beside the point at this time. Okay. So you have a glass tube with a AgCl, couple inside it. Okay. So I'm just drawing this like the glass wall. It's a glass tube. Inside here is electrolyte KCl. Okay. Now, it's critical that there's electrical ionic connection from the reference electrode to the main solution, from the reference electrode to the working electrode. Right? Somewhere over here is our working electrode, right? We have whatever our working electrode is, some platinum foil, some RDE, whatever it is. There has to be connection ionically between the reference electrode and the working electrode. But we contain the reference electrode usually in a tube, so that it has a nice stable potential, because the potential of this AgCl is determined by the concentration of chloride ions. And usually we do 3-4 molar KCl, something like that. Okay. So that's why we have this. And so we have to use this frit. This frit right here basically blocks bulk diffusion between the inside of the reference electrode and the bulk solution. That is what is associated with typically the amount of impedance. The frit has a resistance associated with it. And it's usually somewhere between 1 and 10 kilo ohms. Okay. Now here's why at high frequencies we have a problem. We have a problem with this, and why it causes issues with the potentiostat. Okay. The connection that we have in solution here is such that it goes through this Ag wire, which is perfectly conductive. There's no resistance, basically, right? Through high concentration electrolyte, and then through this frit, this resistance, which has this much impedance. Okay. If there is any other pathway electrically of communication that has lower than 10 kilo ohms or 1 kilo ohm of impedance, the potentiostat will select that pathway, right? Current, electrical communications in general is like water. It will follow the path of least resistance or least impedance, right? What we have in a very weird counterintuitive way is through the glass wall of our reference electrode. This is just a zoomed in version of the reference electrode, right? Okay. Through the glass wall, we have KCl here. We have whatever our electrolyte is over here. I don't know. H2SO4, whatever it is, doesn't matter. We actually have, this is glass, right? It's some glass body. We actually have a capacitor here. Okay, we have electrolyte on both sides, and we have a material separating them. That's glass. Glass has a dielectric, and it actually is a capacitor. So what happens technically at high frequency is that there is an alternative pathway. So again, I'm gonna draw this more of as a circuit down here. So we have AG, AgCl, AG wire, right? And we have to have communication in solution, making it to our working electrode. And so I can either go through the frit and make it to my working electrode, or I can go through the glass capacitor and make it to the working electrode. So what I actually have is a circuit here, right? I have a resistor and a capacitor in parallel. Now, a resistor and a capacitor in parallel, again, I go to a lot more detail of this in like a webinar, so I'm gonna try to go through this relatively briefly. And if there's confusions about that, I have a more detailed explanation in a webinar. Let's just say this is 10 kilo ohms. That's a resistor. That value does not change. It's determined by this frit in the condition of the frit. The impedance of a capacitor changes based on frequency. The impedance of a capacitor is big at low frequency and low at big frequencies. It's inversely related. What that means is that at high frequencies, the impedance associated with the capacitance through the glass directly can be lower than the impedance of the frit, which means the potentiostat is going to pay attention to this sentence. At high frequency, the potentiostat is trying to communicate directly through the glass wall of the reference electrode. That can't really be done, right? So you get odd results. You basically have no real communication between reference electrode and working electrode at those frequencies in that situation. Okay. I'll do this mathematically very quickly for you. The capacitance of a capacitor, very generally, is equal to the dielectric constant of the material, in this case glass, I'll just put Eg, times the dielectric constant of the vacuum permittivity. Okay. What is it? A over D, right?
Yeah. Area over
Distance.
distance.
The surface area of the plates essentially over the distance separating them. Okay. Now, I'll plug in some values for you. So a typical reference electrode, this is just an example. The thickness of glass, it might be about 2 millimeters, something like that. Thickness of glass. Okay. The surface area is going to be however far you have this thing dipped in solution. Let's just say my length that I've dipped it in solution, I think maybe 4 centimeters or something like that. So let's just say I've got 4 centimeters of length. The diameter, overall diameter of my reference electrode might be 1 centimeter. Okay. And so the area exposed, forget about the tapered, it tapers down. The geometry is actually quite complicated. If I just assume a cylinder, I would have the overall diameter times pi times the length. That's a rough estimate of the exposed surface area, right? At a quick glance here. Okay, so that would be roughly equal to the area. Now, if I plug in numbers here, I have 1 centimeter diameter times pi times the length of dipped in, it's 4 centimeters. The dielectric of glass is about 5. That's just what it is. You can look it up if you want to. The permittivity of a vacuum is about 8.854 times 10 to the minus 12. These are all SI units. This is like farads per meter or something. So converting everything to meters and plugging this in, okay, you get something, depends on these values, you get something like 20 picofarads, something like that. maybe 10, maybe 20. It depends, right? The exact number of picofarads. Okay. Now let me share with you software. I'm going to open a different version really quickly here. This one. Let me show you what a 20 picofarad capacitor looks like. Okay. So I know you can't see the pop-up. I'm just putting a thing really quickly here. All right. So this is a constant phase element, so don't worry about that. So if I have, for example, a 20 picofarad capacitor, all right, at the highest frequencies, at a megahertz, okay, this is the list of impedance values by frequency. So at 1 megahertz, for example, and this is just one particular set of values here, at a 20 picofarad capacitor, the impedance is about 8 kilo ohms. And then at whatever, just 900 kilohertz, it's 9 kilo ohms, and then as I get down 700 kilohertz, I get to 10K. Okay, so the point of this is at the highest frequencies, and it depends on the value of my capacitor, I have values here of impedance that's under 10 kilo ohms, just for the example that I used. So what's happening at high frequencies, in conclusion, is that the potentiostat is sensing a capacitor. I know it's an odd thing to think about through the glass being a capacitor, but it technically is. It's trying to sense an impedance through the glass wall that's lower than the impedance of the frit itself. And so that just leads to bad results because there's no real diffusional ionic connection there. Okay. And so that's effectively what you get. You get these odd artifacts and these weird things. Now, conversely, when the frequency is low or it's DC and it's like no, frequency is like 0, you can think of, or hertz, small, the impedance of trying to go through the glass wall is huge. It's like giga ohms or whatever. It's like the potentiostat won't try to communicate. Even if the frit is somewhat blocked and not doing a good job, it'll still be lower impedance than, through the glass wall. It might cause other problems. My first answer to your question was something like it affects how the potentiostat communicates, and it can affect the, you'll see odd effects if you have a really high impedance in your reference electrode, even in DC techniques. But I hope that's relatively clear for you. What you have a resistor and a capacitor in parallel. The pathway is going to pick whichever one of those is lower impedance. And at high frequencies, in some situations, going directly through the glassware is actually lower impedance. And so you get that kind of odd artifact result. And so that's the technical answer to your question. Sorry, that took forever.
No, that's all right. I think the only thing I would add to that is that capacitors, like resistors, just by themselves have no phase delay.
That's right.
And so by virtue of being a capacitor, because there's a huge input impedance on the reference electrode through the electrometer in the potentiostat circuit. And so you got like 10 to the 12 ohms of input impedance, no matter what. But it's really the capacitor's phase delay that like screws things up. Like the fact that the time it takes is delayed or offset will affect DC as well as AC measurements. So that's another important distinction about if you had just like a super high resistance, no problem. But the moment capacitance gets involved, it causes time variations, which is a distortion.
Yeah.
Okay. So we have a question. We'll try to get through some of these relatively soon. So Cross Hero says, "Hi, I'm doing electrodeposition of looks like copper oxide on TFO substrate with a platinum counter electrode. I'm not sure how to know how to start with which method. Should I use galvanostatic or potentiostatic method?" And he is using Cross is using a silver chloride reference electrode. My recommendation, if you were starting out, is to do a potentiostatic experiment. Specifically, I would do something like cyclic voltammetry, because currently you don't know at what potential does copper oxide deposit on the FTO substrate. You may even want to just do cyclic voltammetry of FTO in your electrolyte itself, because you don't know what your electrolyte's going to do. So by doing experiments potentiostatically, such as cyclic voltammetry, you'll get an idea about, like, okay, what are all the things in my system that could be affecting the electrode deposition process. So that's my recommendation of where to start. You start potentiostatically, and then once you kind of understand, all right, this is where the the potential is, and then I can start doing galvanostatic experiments and try to adjust the rate and make sure that, oh, the potential I'm measuring in a galvanostatic experiment is near the potential of the I'm assuming the electrodeposition is a reduction reaction of copper oxide on FTO. So then you can see where that peak is, what that potential is, and then galvanostatically, you can verify, oh, the potential I'm measuring galvanostatically is at the potential. And then during your galvanostatic experiment, if you notice the potential moving around, well, you know it's no longer doing that deposition, and then you can turn it off and then evaluate your system. So that's my recommendation. All right. Okay. So just moving along.
Great name.
Yeah.
Physics tutor.
Physics tutor. Ah, I see what I was doing there.
I used to spell physics in college that way as a joke. I like it.
Nice. Can you please say me which is the best reference electrode to use? Is it silver chloride or calomel? And then there's some other kind of questions and stuff. Here, while we're at it, he has another question as well just after, which is it always correct that the potential window for CV and the voltage getting in charge discharge curve is always similar? It's funny because you talked about that in the last live stream, but in general, it depends on your system. I personally like silver chloride. It's less expensive. It doesn't involve mercury. As long as you're using chloride ions, I mean, it's relatively simple construction, and it really depends on what your system is. Although calomel is very, very stable. So if you're doing an experiment that's extremely long, you might want to pick a calomel electrode instead. So that's kind of I think it's more of a personal preference, and then see like what your electrochemical system is. So that's my recommendation for that. And I think based on what Neil said last week, is that the potential window for CV and the voltage from the charge discharge curve should be similar. There is Neil was mentioning last week, there's a little bit of an arbitrary nature as to how we define the potential window, and that, oh, you can, you say, oh, I'm starting to get like an up curve, so my potential window is here, but like, well, what's the real current that you're measuring at that level, and or at that potential, and where are you in your charge discharge curve for your battery? So so those are some things to think of. But yes, I would say generally speaking, they're the same. All right, moving on. Just kind of a quick thing. It's my project from Ayob. It's my project to create a little instrument in cars. How to break CO2 and benefit from C and O2. Good luck. It's a very hard project. There's a lot of people working at it, and Ayob has a few other comments below, which is that he's this high school student and wants to know how he can communicate with scientists to share information. So I think we can just briefly speak about this quickly, so we can answer all of Ayob's questions. This is something, personally, I'm going to say it's something that takes time. to really learn how to communicate with scientists. You need, whenever I'm talking to any scientist about anything, asking questions, understanding the material from a very base level. Like, we're talking about electrochemistry because both Neil and I have a background in electrochemistry, and we understand a lot of some of the fundamental things. So when we talk about things like resistance and capacitance and stuff like that, we know inherently what we're talking about. So using the terminology of using the terminology used in the field is very important, and describing it as clearly as possible. I know it's just like, how do you communicate clearly? You just communicate clearly, but yeah, it's like, if somebody can, you know, it, I would say throughout your training, high school, college, if you decide to go to graduate school, um, you will always meet new scientists who will push how you communicate science and demonstrate, like, oh, when I tell somebody this about my science, they're going to say, well, this is clear or this is not clear. And you'll start to, over time, get a better idea as to how better to communicate. But these are really good questions. Maybe if there's time at the end, we can spend more time talking about it. But there's
Yeah,
a lot of questions.
I would add to that you know, first of all, some of these things are tricky. In particular, if English is not your first language, most of, I shouldn't say all of the world, perhaps, but a lot of the world communicates science in English, right? And so, if English is not your natural language, or for whatever reason, just this is just general advice, that can make communication, of course, a little bit more tricky, because now you're dealing with a language barrier in addition to scientific terms,
Mhm.
right? So that just makes things a little tricky. I think the first thing I'd say is practice, like you were saying, right?
Yeah,
Just
takes time.
don't
Just
be
doing it.
afraid to. And this is a good example. I mean, thank you for coming and asking us questions.
Mhm.
I think don't be afraid to ask questions. Don't be afraid to to ask whether online or in person. If someone dismisses you because you're a high school student, then that's shame on them. That's not on you. That's not your fault. Um, I think that, unfortunately, there is perhaps a propensity for scientists and academic folks who are, maybe well established in their career, to be a bit arrogant. I'm trying to be kind here, but
Yeah.
that's frankly the truth,
Mhm.
and I don't care for that. I mean, we all misstep from time to time, but I think that humility is important, and science is for everybody. Science is ubiquitous. It's it knows no bounds or cultures. We're all, as a species, learning more about the world around us, and this is not um, you know to be safeguarded and think that you're above someone else asking. I just say all this to try to encourage you to not be discouraged, by someone who thinks it's, well, what's a high school person asking these questions for? Why not? I don't. What does it matter what your characteristics are or your age is? I think it's very important and impressive at any age, particular younger ages, to be willing and to go out there and ask those kinds of things. And then the other thing that I'll say is that don't be afraid to speak clearly and simply, even when discussing complicated things. I have a very strong preference towards, if possible, and it's hard, especially it's this kind of thing that we do when we talk about electrochemistry. We have to use a lot of technical terms a lot of the time because it's just part of the process. It's part of our field and our profession. Electrochemistry's got a lot of jargon in it, like everything
Mhm.
else.
Yeah.
But I just try to, whenever I can, speak with simple terms, because there's things that people, even experienced scientists, can understand simple, normal language. You don't have to always try to make your sentences, sound as complicated as possible. You know, I think that's another one of those things that people in all scientific fields tend to do sometimes is they want to sound smarter. So they try to, you know, again, there's a difference between having jargon and terminology because it's part of the discipline.
Oh,
And
yeah.
it's another to like intentionally chalk what you're saying full of that stuff, you know, like
Oh, yeah.
to
Yeah.
sound smarter. It just turns people off. So don't be afraid to like just use simple language if you can, you know, like I stuck the electrode in the solution. It's like you don't have to be like, I carefully arranged the coordination of the working like just,
Oh,
I
yeah.
dumped
Yeah.
the platinum wire in my beaker and then I hit go on my potentiostat. Like, you know, like I don't know, sometimes the simple language really helps connect people because it's like, yeah, I understand what you're talking about, you know. You don't have to be so complicated to try and impress folks or something like that. That's kind of my other advice I'd give.
Yes.
Anyway.
No, that's very true. It's a journey.
It is a journey.
It's a journey. So I guess kind of going down the list, Gangster has another question. How will the equivalent impedance circuits, and I don't know what hodographs.
Yeah, what in the world is a hodograph?
I don't know what a hodograph.
So
is.
I Googled it and it looks like it has to do with weather.
Yeah.
Like so the Wikipedia answer tells me, or the Google answer says, a hodograph is a line connecting the tips of wind vectors between two arbitrary heights in the atmosphere, or it's a diagram that gives vectorial visual representation of the movement of a body or fluid. So the short answer to your question is I have absolutely no idea. I don't know what a hodograph is in the context of impedance, electrochemistry, RDE, or quite literally anything else.
Yeah.
So I'm very sorry. I honestly cannot. I have no clue. I have absolutely no idea what a hodograph is.
Yeah.
I cannot.
I
I
don't
simply cannot
either.
answer this question. I'm very sorry.
Yeah. Yeah. If you want to elaborate, Gangster,
Yeah,
if we have time, we can try. Let's see. Let's see.
All right. Looks like
Veer Shaw has a question. Let's see. It looks like it's a question from an exam specifically. Just the way it's worded.
yeah, is this a G exam question?
It may be a G exam question. Consider the electrochemical cell with A as a solid with AN. I don't know what N, if it's a different. Oh, yeah, it's probably different material. 2 molar, and then you have B2N, 1 molar. B is a solid. Okay, yeah, so you have this salt bridge thing. The value of delta H 0 for the cell reaction is twice that of delta G 0 at 300 degrees. If the EMF of the cell is 0, the delta S naught in joules per Kelvin per mole of the cell reaction per mole of B formed at 300 degrees is blank. This is a relatively specific question.
Yeah, you're just asking a question that you have on your entrance exam, aren't you? That's what it seems like.
Yeah.
I'm not sure that we really.
I'd have to think about this for a bit to really try to understand, because it's not like you're really given any numbers. You only know that actually, all right, so okay, you know that E naught is, well, I can at least, maybe I can talk about what I'm thinking about.
I think it's just G over T.
G over T.
Yeah. So G is equal to H minus TS.
Yeah.
Right. And it says H is twice G. Right.
Yes.
So H is twice G. So that means the equation is G equals 2G minus TS. Subtract 2G from both sides. You get G is equal to T times S. So solve for the entropy. Entropy is equal to G over the temperature in this case. So whatever G is divided by 300K. I don't know if you have an answer for G. Anyway, I think we've been getting a lot of these, questions to a certain extent.
I was going a slightly different route. It's
what do you
I was thinking that you know that I think they're saying that the cell potential is 0. So you have
Oh,
an
you gotta use it.
expression for G in terms of
What NFE?
like NF. Although that in and of itself doesn't work ultra well because
And G is 0.
then G is 0.
So then S is 0. Like it's probably not all 0.
Yeah, it can't all be 0.
The EMF of the cell, that doesn't mean, is that, I mean, terminology wise, is EMF the same as E0 in this case? Or are they saying like E minus E0 is like,
oh, so this
I don't know. I don't 100% know. Yeah. I mean, I don't want to delve into this too much, to be honest. Like, I think to be perfectly honest, there's a bit of a,
you-
just answering G questions, entrance exam questions is a bit perhaps beyond the spirit of this kind of live stream, to be honest. That's my opinion. I don't know, you might feel differently, but it's kind of like we're helping you with your homework. It's a bit odd to me. Got the answer. Oh,
You got the answer.
yeah, G is minus,
I got the answer wrong. Got the answer. Thank you. G is equal to
minus
minus
NFE.
NEF.
Yeah.
Oh, G is equal to minus NFE. That's not none of those things.
Yeah,
That's just another expression of the. That's just another expression of just Gibbs free energy. It's not
well,
useful at all.
You just said that you got it, so I think we're going to move on from this.
Okay.
I think perhaps, yeah, it seems like you've maybe got a grasp on it here, but
Okay.
yeah, I'm not so sure that we want to be tackling exam questions, and frankly, it's like, I don't know. I personally feel like
they can ask us anything about electrochemistry.
Is that electrochemistry, or
it is electrochemistry?
I guess it's sort of electrochemistry.
Absolutely,
well,
it's electrochemistry.
I'll just be honest. I'm like too far removed from thermodynamics classes to give you smart answers here.
Yeah,
like,
I am too.
I know G is H minus TS. I know G is minus NFE, and then these kinds of questions are often, they're hard. Like it's hard for a reason, and there's other stuff you have to think through. And like, I feel like I'm personally, I don't speak for you, but like for me, I'm like spitballing on it, and I might be very well missing a pertinent piece of information. I don't want to give you wrong answers on these kinds of things, and you probably don't want to watch me flounder trying to remember thermodynamic concepts and things like that. I don't like, deliberating on entrance exam questions. I think it's a little bit beyond my capability to give you the right answer for one, and and in a reasonable amount of time. That's
yeah, that's right. We won't. It'll be very difficult for us to answer this question very completely.
Yes.
All right, let's move on to the next one. Let's see. Shen Sensen is asking, are you familiar with any work on GQD doped GC electrodes for sensing, TIA?
So I looked this. I think that means graphene quantum dot. I think that's what that means. QD means quantum dots. I'm not, to be honest.
I'm not either.
Yeah, I really don't know. Yeah.
Yeah. Sorry, we don't know.
The best I can say is that it's pretty common to have deposition, either electrodeposition or film, made on glassy carbon electrodes to, check for electrocatalytic activity, including sensors and whatever, a lot of different kinds of things. I don't know enough about the morphology or the structure or the activity of quantum dots or graphene quantum dots or anything like that. But just other than to say, I would imagine it's an effective catalyst for a lot of things. Seems like it's a special morphology, probably has a tremendous surface area. Quantum dots is probably small and whatever. But I don't have any firsthand kind of experience or knowledge of it, to be honest. So sounds interesting, but I don't know.
Mm-hmm.
Yeah. Oh, Race has clarified that. So the question that Race was asking was drift correction.
Yeah. Drift correction in the EIS.
I'll draw this for you. Hang on, Race. So generally speaking, drift correction with respect to impedance is something like this. Okay. Hang on. So if you have the raw data, like a sine wave, right? So if I'm applying, let me do E versus time, right? Ideally, right? Let's whatever my set point is. Ideally, I would have something like this, right? So if my sine wave is like that, everything's all happy and good. Drift is when, right, it starts to do something. I'm trying to draw the same frequency, but you can see that it's drifting. So it's like it's got a baseline that's moving. So drift correction is something. Now everybody kind of handles this differently, and it's something that either people do either manually or some potentiostats will do it. Basically, it's like you're turning the red into the green. You correct for a baseline, right? And so you sort of raise up the baseline to correct for the drift. The Lissajous, if you have a potentiostat or something that shows you Lissajous, you might see normally you'd get a nice whatever oval or something, and the drift, if you're watching, you'll see like what looks like a slinky. You might see something that looks like this. If it's drifting, it might drift like straight down or this way or this way. I've just kind of drawn one direction, but something like that, you'll see that's like a drifting kind of a phenomenon. It tends to happen if you have some other process happening. It's not stable. It can happen at really, really low frequencies because you'll have diffusion, you'll have, it takes longer. So instabilities can take over. I'll just say two things about this. The first is that this can be an effective way to like clean up your EIS data in the case where you have a lot of drift or whatever. The second thing is that it fundamentally violates the conditions of impedance. And so I have a problem with it philosophically, but I understand why people want it. Fundamentally, impedance requires linearity, quality, and stability. And if you have a drifting baseline, it is at least one of those things is not true. Probably two are not true. It's not linear and it's not stable. So when you're correcting that, you're just lying. So I'm a purist, I guess. I don't know. I don't like it. I don't like the concept of fixing something that's happening. Like if it's drifting, it means it's not stable. It means you can't fundamentally, by definition, acquire proper EIS data. But you can if you adjust the data and lie about it. I won't belabor this point. You can see where I stand and how I feel about it. But that's kind of, I think, for the most part, what people are doing when they're talking about drift correction for impedance.
Mm-hmm.
Where are we at here?
Just kind of going up and down, back and forth. There's one from Muhammad Umar, which is state Kohlrausch's law. And I looked it up, and Kohlrausch's law states that the equivalent conductivity of an electrolyte at infinite dilution is equal to the sum of the conductance of the anions and the cations.
Exactly.
And that is Kohlrausch's law.
I don't know that.
I've never heard of that before.
I don't know that one. But you did what was asked.
But I did what was asked.
You stated Kohlrausch's law. I would have done the same thing.
Yes.
And that's it. That's an easy question.
That's an easy question.
That's just a demand. It's a demand, and we've successfully done the demand.
We've done the needful.
Okay. Yes, that's correct.
The guy's asking,
can you
store zinc and copper sulfate? I don't know.
What do you mean by store? Copper sulfate? Like copper sulfate is a salt that dissolves in water. Do you mean like a copper sulfate solution? And I don't know what you mean by store exactly. I guess I don't really understand this question, to be perfectly honest. Like if you're thinking about electrochemistry, you can have a copper sulfate, right? Like an electrolyte, it's blue for what it's worth. And, you can add a zinc salt to it or something, or like, I kind of don't understand the spirit of the question in a sense. I guess we might need some clarification.
Yeah.
It sounds like you mean something a little more specific than what I'm saying. It doesn't seem like it's that simple. I don't really quite understand. So
yeah.
So maybe you can clarify.
Yeah. All right,
Okay,
moving on. We have some more from physics tutor. He's asking, actually, I'm trying more, but not getting the same voltage in CV and GCD plot. Please help me getting that. And then he also says, also, I have high IR drop in CD,
Charge discharge.
charge discharge plot. Please help me to reduce that. I'm assuming all this stuff is for a battery, so that's always the thing that
Or a
confuses me.
supercapacitor or something.
Yeah, because IR drop is mostly a thing that exists in. It's not the case with batteries, or at least their impedance
It's
is
not often
super
the
low.
case, but yeah, I mean, I guess if you have like some aqueous battery or liquid system or something,
Mhm.
it is, conceivable you'd have I don't know, appreciable amount of IR drop, I suppose. To extend that, usually batteries tend to, again, if it's a battery, I don't know if it's a battery exactly, right? But
yeah.
batteries tend to have higher currents. So if you have any appreciable amount of R, the IR drop will be a lot because I is high,
Yeah.
it's possible.
Yeah, that's true.
Correcting for IR drop, a lot of most potentiostats have the ability to correct for IR drop in most experiments, like if you're doing CV or I think even chronopotential. I guess it depends, right? I don't know if
Mhm.
you're doing like chronopotentiometry is charge discharge. It's just that's like the technical name. So it's like, for
Mhm.
example, if you're working with like a standard potentiostat and not a battery cycler, maybe you should be able to do chronopotentiometry and do IR compensation. I don't, again, I don't really know what you're working with. Perhaps you don't have that ability, so that would be tricky. And then more simple kinds of battery testings, that cyclers that do charge discharge kinds of tests, I don't know if they allow IR compensation or not.
No, he's working on a supercapacitor.
Supercapacitor, okay.
Liquid electrolyte with glassy carbon working electrode. It's a supercapacitor?
Yeah, glassy carbon for a supercapacitor. Interesting.
Interesting.
Well, that probably explains why you have decent amount of IR drop compared to like a battery cell. But yeah, I mean, doing uncompensated resistance is the best way to help combat high IR drop if you have that ability with your potentiostat. Otherwise, you can correct for it afterwards. It's not ideal, but you can.
You can also reduce the IR drop by increasing the electrolyte concentration
Yeah.
or minimizing the distance between
working in
the
reference.
working and reference. Those are like physical things that
exactly.
you can do.
Yeah, that's a good point. I should probably mention that. But if you're gonna try to, you can correct your data afterwards. I mean, it's correcting the voltage data by subtracting IR. So if you know what R is, maybe I'm just assuming you know what the resistance is. So you said you have high IR drop, but you know what R is in theory. And especially if you're doing charging, discharging, probably means you have a constant current. So I is fixed and R is fixed. And so IR is fixed. Let's just say IR is, right, some number of millivolts or something. Then technically you can just subtract that from your voltage column, right? Like at the end of your experiment, you have probably voltage and time, right? You have like the time, which you might convert to a capacity or something, and a voltage column, like in your Excel sheet or your Origin or whatever software you're using. The IR corrected voltage would just be that voltage minus IR at every point. That's a post experiment way of doing IR correction. It's not ideal for a few different reasons, but you can do that. So that is one way to account for it in your data afterwards if you want.
Let's see. Okay. I'm trying to.
Hoda graph is a Nyquist diagram. I've never heard that term for a Nyquist.
Yeah,
plot.
me too.
Interesting. So that actually looks like there's a clarification.
Yeah.
By Gangster here. So yeah, thank you for clarifying. That term is not something I've ever seen before. It's not, I don't believe it's used in the context of impedance very often. So thank you for clarifying. You wanted to analyze the differences between the equivalent circuit
And the Nyquist plot.
and the Nyquist diagram for oxygen reduction reaction on RDE and on a simple electrode.
So he just wants to know what's the difference. Like if I had an RDE and I had a regular, I'm assuming stationary
Like what's the
electrode.
difference between RDE and a stationary one?
Yes.
Because there's, I think, yeah, the wording here was kind of throwing
Mm-hmm.
me for a loop a little bit. Sorry about that.
Mhm.
I think that's what you mean, gangsters. What does the Nyquist plot look like for stationary versus rotating? I can show you. If that's what you mean. If that isn't what you mean, please comment and stop.
Yeah, then you need to clarify a little bit more.
But I think what you're asking is what's the difference? What is the Nyquist plot difference for RDE when you're rotating and when you're not? In short, it's this. Stationary ORR. Writing is really hard. I should just use the text thing. RDE ORR. Oh my gosh, that's supposed to be an R. Okay.
Yeah.
Got it. Promise.
Mm-hmm.
There you go. That's the difference. That's the answer. You basically get a Warburg short. And you'll get this start to decrease in width, the semicircle, as RPM increases. It goes this way. There's like 1,000 arrows here. Sorry.
Mm-hmm.
As RPM goes up, this red curls down and then gets the semis to like the width. Like if this is a width, right? This is sort of, you could think of this like a width of a semicircle, sort of. It gets smaller as the RPM gets higher because it's directly proportionate to the diffusion layer thickness. As you rotate faster, the diffusion layer thickness shrinks, which means the width of the semicircle gets smaller. There's lower resistance because the diffusion layer thickness is smaller. Stuff gets to the electrode quicker. That's why you get higher current. So clarify if that isn't what you were asking. I think that's what you were asking, and that's the answer.
All right. There's not a whole lot of time left.
Yeah, we'll try to get to everything again.
There's some of these questions.
More G questions.
Yeah, there are a few more G questions, but there's a question from Cross that I think we can answer relatively quickly. Sorry if we're skipping some people. It's just time and things like that, as well as our ability to answer the questions. But how important is the distance between the working and counter electrode, especially when O2 gets produced on the counter electrode? I'm using a small crystallizing dish, 4 centimeter in diameter, to minimize the electrolyte usage. And how near should the reference electrode be to the working electrode?
That's a good question.
So those are all good questions. So generally speaking, for the distance between the working and counter, you can keep those fairly far. The important thing to keep in mind is that if there's a lot of resistance between your working and your counter electrode, you will run into what's called a compliance voltage issue, which means that you may want +1 volt between your working and your reference electrode. Well, that is established by the counter electrode driving voltage and current through your electrochemical cell. So if it's really hard, if there's a lot of resistive elements between the counter electrode and your working electrode, it's not going to be, there's a chance it might not be able to reach that voltage that you've set it to. So that's really to say that the resistance is important. But if you are worried about, say, oxygen that's produced on the counter electrode affecting things that are happening on your working electrode, then yeah, you can separate them in such a way, as far as you need. But it's that resistance between the counter and working that that becomes important, problematic. And then lastly, how near should the reference electrode be to the working electrode? One of the rules of thumb that people often quote or say is it needs to be, I think it's about 1 diameter or 2 diameters in length. So the working electrode diameter, the reference electrode needs to be at least 1 or 2 of those diameters away from the working electrode. That's if you have a planar working electrode disc. And I know you have, you're using a crystallization dish that's like 4 centimeters in diameter. Or no, that's just to minimize electrolyte usage. So you're able to position things on a crystallization dish with a very small amount of electrolyte. But the reason why the reference electrode should be that close is if it's too close to the working electrode and you're doing analytical experiments, you will mess up the pathways of diffusion that are happening on the working electrode. You may also mess up a little bit of the sensing of the working electrode or of the reference electrode with the working electrode. And so those are kind of the rules of thumb that are used for positioning the reference to the working electrode. I hope that was helpful.
Looks like there's a lot of questions from Peachy Peach here. I think this one is a bit. This zinc copper cell concentration is 10 times the expression delta G. I don't even think there's a question here. This just looks like the start of a copied like exam question of some kind. The expression for delta G in joules per mole, and then there's nothing. So I'm going to sort of move past this, I suppose.
Yeah, because the question then is like,
what
is the working of SHE? Like that's not really a question, sort of to say. Like it's the standard hydrogen electrode, and it's a reference electrode, and that's So
this next one's fine. What's Faraday's law of electrolysis? This is kind of a simple one to use to calculate, like we've been talking a lot in this live stream, actually, or at least a couple of times, about, for example, you're doing galvanostatic to have the rate of something being formed on the surface. And so Faraday's law of electrolysis is just, so it works off of Faraday's constant. So Faraday's constant is 96,485.3 coulombs per mole of electrons. Let me get the right form, before I write something stupid. Faraday's law. I just want to kind of illustrate. You want to, let me see here. Electrolysis. I want to get the right thing here. Again, sorry about this. I just want to make sure I don't write something silly.
No, just like figuring out how much mass of something.
Yeah, that's kind of how it's. I use it, or it's used for the most part, right?
Yeah. The mass of something is equal to the current times the time, so that you have charge,
right?
And then
it's the charge. Yeah, it's the charge. I times the time. So that's charge, right? Which is coulombs.
Yep.
Divided by F, and then there's a stoichiometry in here,
and that'll give you moles.
And that gives you moles of electrons, and then you're going to multiply by
molar mass.
X moles of electrons. Excuse me, wrong one. X moles of, species A times Y moles of electrons, and then times the formula weight, whatever, K grams per mole. So this is effectively Faraday's law of electrolysis. You apply 2 milliamps for an hour. Okay, that gives you a certain amount of coulombs. You divide by Faraday's constant, you get moles. You get 1 over moles of electrons, so mole of electrons. And then I have an expression like A plus 3 electrons gives me B, whatever. So for every 3 moles of electrons down here, I have 1 mole of A. So I have to use the stoichiometry conversion between the moles of electrons and the moles of the species that's formed, or whatever. This would be B dot A, whatever. And then I multiply by grams per mole or kilograms per mole, whatever it is. And that's how I get the mass that was formed. Basically, it's a way to get how much mass was made by how much charge was passed. So there you go. That's effectively what it is. Just like a unit conversion thing, actually, to be honest.
Yeah. I think that's
Okay.
really what it is.
Yeah.
Well, it's been about 2 hours,
Yeah.
a little over 2 hours. So we can try to, I would say we can keep note of what questions were asked and then try to address them in the next live stream next week. So I think we just call it a day for now, because I think there has been a lot of questions and we haven't moved.
Yeah. Sorry if we did not get to a few of them.
Come early next time and ask them.
Yeah. Sorry if we took too long to answer. That is one of the tricky things on, regrettably, electrochemistry is a complicated thing. It takes a little while to explain stuff sometimes. So I do apologize if you ask a question, you're waiting a while and don't get an answer. So it is, we do our best to get through everything. And unfortunately, sometimes we reach the end of the time.
Yeah. But we'll be back, next week. Post your questions there if we didn't get to them.
Yeah, put them into the comment of this video. This will be a video living on our YouTube channel, so please put the questions there. We'll ask it. We'll answer it in the, in the comments, and also if you want more discussion of it, we'll start next week talking about it. Right?
Yeah,
as best with the time that we have available. So, So anyway, thank you for those showing up and saying we're magical. We try.
Yeah. That's good.
Yeah, we appreciate it, but we're not magical. We're just trying to help and engage the community, I guess. But anyway, we'll call it a day. So again, thank you everybody for joining us. We'll see everybody next week, next Friday, same place, same time, and have a great weekend, everybody.
Yeah. All right. Bye.